treat to hear me play. So is this right? This was a collective presentation.
This is correct. That is correct, and we can see it. Yes, thank you.
Okay, so talk about in-network collective communications through here and what we've done specifically in LIBFABRIC. If I can move the mouse. So the focus on this talk is really looking at how do we enable this technology. And again, the technology could be accelerations and switches, which is a common focus area, but also what we have for NICs, what we may have in platforms or FPGAs. For example, you could have FPGA attached to switches in the network. So we're not really caring about how this is implemented. We want to be able to enable the technology regardless of the implementation. And one thing I'm not going to look at is discussing how effective these solutions are. So I'm not going to look at any performance type information or talk about whether the applications can truly benefit or not of these. It's really trying to make sure we enable these technologies for the applications. So for the maybe one or two people on the call who don't know what collectives are, I do have some introductory slides, just 2 or 3, that talk about what collectives are, how they differ from other types of operations. And really part of that is to set up what we're looking for in terms of network accelerations. And then move into the software abstractions to how to get an application to be able to access this in-network acceleration. And the software abstraction kind of broken up into 3 different parts. To identify who the members are, the collective, how do we set up the communication, and then how do we invoke the collectives. So I have kind of architecture for that, and then a couple slides on what the code would actually look like from an application level. And then come back is look at where are there gaps. So from what we have, there are some gaps we've seen, and how do we address those gaps? So I have like one proposal, but a lot of this would need more discussion in the open source community to figure out where do we have these types of gaps and how do we assure that we're providing an efficient implementation, mapping from what the application needs down to the hardware. Was there a question? I can't see the.
No, there's just a request for you to have a halftime show next year.
Oh, okay. So how do collectives differ? So to start with, I'm looking at really look at multicast versus a collective broadcast call as a kind of a comparison starting point. And here I'm showing what we have for multicast, which most people would be familiar with. So in this case, I have 3 endpoints. These are datagram endpoints. So they're unconnected, they're unreliable. In this case, the application, all the peers make a call to basically join the multicast group. And then you have one person in this case who's doing a send on the multicast group, and then everybody else who's trying to receive the data. And with multicast, there's several things here. The sender doesn't know who's actually receiving the data. So he's just doing a send to the multicast group, and then it's going out into the network. Since we're dealing with unreliable datagram communication, the data itself is limited to a single MTU usually. So maybe 1,500 bytes, 2K, 4K, that'll hit the network. So what we want from the network in this case is basically packet replication. It needs to take that send packet and then send it out all the outgoing, for example, switch ports to the endpoints who are trying to receive it. So in this case, we have the top guy, he did the join just fine. He posted some receives, the send matches that receive and comes in just fine. In the second case, we have the endpoint here had some receive buffers already posted. He joined the multicast group and then posted some more receives, but the multicast send actually landed into a buffer that was posted prior to the joining of the multicast group. So there's no coordination here between the sender and receiving buffers. And then the last guy was kind of slow. He didn't get around to joining until after the send had occurred and then never saw the data. So this would be kind of a general setup that we have for multicast. For collective broadcast, several differences here. So we start with, in this case, reliable datagram endpoints. So now we have reliability built into the transfer. Again, we have the 4 endpoints, our peers, they all do the join call. In this case, the joins are actually coordinated. So until everybody joins, we don't continue. So now we have at least everybody who's active in this collective call. And then we have a send. In this case, we have 1 sender, 3 receivers. Because the join collective was coordinated, the broadcast send knows who's going to receive the data. So it's going to send the message, but it knows who it's going to. It knows in this case there's 3 receivers. And then the receives are actually coordinated with the sends. So they receive from, in this case, they know exactly which broadcast, who's doing the send, where the data is coming from, and they would even know, the size of the transfer. So one of the changes here is now we're dealing at a message level. So we're dealing with reliable datagram. So not just an MTU, but an actual message. And then we have acknowledgements that need to come back because we need reliable delivery. So what we need from the network in this case is message replication. So we're not just sending packets out, we're actually sending the whole message out. We need to have ACK coalescing. So if we send the message to these 3 peers, we can have the ACKs come back, and maybe you could have a switch collect those acknowledgements before sending the ACK back to the originator of the send. And the last slide for that kind of the introduction to collectives. So conceptually, the way we think of collectives, or this idea is I think of them as a multicast atomic operation. So with the collective broadcast, it's actually a little more involved than what I showed in the previous slide. So in this case, we have a peer who's going to broadcast the data to 2 other peers in this example. But we're not just dealing with a message, we're actually dealing with the actual data. In this case, he has an array of data that he's sending. So we know that he's broadcasting not just a message, but he's broadcasting a set of data. In this case, 3 entries in an array. We'll know the data types and the size of this data, and that'll land in the peer memory. Showing here a couple other popular collectives: all-to-all, all-reduce, all-gather. You can kind of see the definition here is kind of by example. You can see how the peers with an all-to-all, you have collections of arrays of data. And after invoking the all-to-all operation, the peers end up with kind of a piece of data from each of the other peers. So peer 1 starts with 159. After the all-to-all ends up with 123 and its response buffer. So we have the same data types that we have with atomic operations. So this could be an int 8-bit, 16-bit, 32-bit, could be a floating point, floating point 16. So we'll know what the values of those are. And then also with like an all reduce operation, we have a set of operations we can perform on the data. In this case, I'm showing a sum, but we could do other type of operations like a multiply or find a minimum, maximum. There's other types of operations I can do here, but those will be very similar to what we have with the atomics. So in this case, I have the peers with 3 arrays of data. I'm going to sum each of those, so I have to collect them all up, produce a sum, and then everybody gets a copy of the results backwards. So the other things we want from the network based on this information is we want data replication. So we're not just dealing with messages, we have the actual data format. That's one of the problems there. Could be we're exposing the data to the network, so we may have security issues. We're going to do computation. Because we're data format aware, we have the ability to do computation either in the switch on, say, an ARM processor, or maybe you have FPGAs attached to the switch where it can do some of these sums. And then we need to be able to coalesce and then distribute the data back to the peers. So like this all reduce operation here, I have to collect all the data from all the peers, provide a sum operation, and then send all the results back to the peers. And that's something that you could probably do with some help in, for example, a switch or something attached to a switch. So from the software abstraction, LIBFABRIC defines a set of APIs to help with this. The steps involved are identifying the members of the collective. That's the first step. This is considered a local operation. The second part is to set up the communication group. This is kind of that join broadcast I showed on the second slide. And then finally, we want to invoke the collective call itself. Go into details on each of those. So identify the collective membership. This is something that all the peers that are participating need to do. And this is considered a local operation, so there's no network traffic generated by this operation. So in LIBFABRIC, the existing API is kind of shown here on the left in architectural sense. It has what is known as an address vector, the AV here. The purpose of the address vector is to take the addresses that are visible to the application. In this case, my example, I'm using an IP plus port as my address that the application sees for each endpoint. These values are going to be inserted into the address vector, and then those get mapped to an address that's specifically for the fabric. In this case, it could be like a MAC address. This could be an InfiniBand lid plus P key plus service level plus Q pair number. Right? There's going to be some mapping that occurs here by the address vector. So the application addresses get mapped into a fabric address that's the application, or that's hidden from the application. And then what the application uses are these, what I call the FI adder T types. So this is an actual type. It's a uint64. In this case, it could be as simple as an index. So each address the application has, they get back an index, and then that index is what's actually passed into the API. So the application will say send to 2. That means this address that maps to this fabric address, which actually goes back to this original endpoint port number 7000 at IP address 10002. So these addresses are what's used throughout the API. For the collective extensions, I have to keep moving my window around here. There's a way to hide it completely. For the collective extensions, we have something called an AV set. This is built off of the address vector. So the address vector set is a collection of addresses. These are peer addresses that will be used in the collective group. So in this case, my universe, when I think of my universe, is going to be addresses 0, 1, 2, 3, up to however many peers I have. In my AV set, in this case, I only want the even numbers. So I have the even numbers in my AV set, and this maps to, this whole AV set will map to a multicast address. Which will be this, get a new FI adder value. So this FI adder value may be something really high, like 10,000. This is really up to the provider to provide this address back. But this address is what's going to be passed into the send calls. And when this address is passed in, that means that that send operation or data transfer goes to all of these peers. The AV set has its own set of operations that it can be performed. So this is kind of an object in LIBFABRIC terms, and it can actually support, insert, remove a single address, but can also do unions between AV sets, intersections, and differences, which is part of the reason it has the name, is it has these set type operations involved. Again, this is just really to set up the operation, or the identify who's going to be in the collective. So starting here at the top, we have our universe. This may be our address vector, and then we create an AV set from that. So to set up the communication, we have our join collective. So this is going to be the first call the application is going to make that actually hits the network. So the join collective occurs over, in, let's say in this case, the example is the universe. The address vector will have its own multicast address, this FI adder. So we'll join with this. All the peers make this call. And then the result is, based on the address vector set, we have a new set of endpoints that'll be in the new group. So in this case, I have just the 0 to 4, just the even numbered endpoints in my AV that end up showing up in the new multicast group. So LIBFABRIC actually has 2 ways of handling this join operation. And they're kind of shown here. OFI manage or application manages it. OFI supports both. The OFI managed one is the application calls join collective, and then the provider basically implements the join call underneath in the provider, which means that the providers are going to talk to all the peers as part of the join and set up the communication group. Once the join call completes, that's when they'll get back, the application will get back this address that can be used in subsequent calls. The other model is an application manage. This means that the application above LibFabric or the middleware has already set up the the collective. So they've already done this collective and they just need to tell LibFabric that the provider that I have the collective set up, here are the members, and here are the resources that we've already reserved. So this allows the application to talk directly to, for example, a Fabric manager to allocate resources and then just convey that resource down to LibFabric. So kind of an example flow that we will look at here. So from the application, if it wants collective support from the provider, it just adds this capability bit, says FI collective. The provider is going to respond back saying, yes, I support collectives. So the application sets this capability. They pass in these hints to GetInfo. GetInfo returns a list of, here are the providers that actually support collective offloads of some sort. The application allocates whatever resources they need. And then we have a query call so the application can see what are the restrictions on using these offloaded collectives. In this case, the application is saying, I need to perform a sum. My data type is floating point numbers. And I want to do an all reduce operation. Can you support this offload? This case, the application is doing a SERP, but it's coming back from these attributes. Yes, I can do an all reduce on floating point. This count here is saying I can't take a data array larger than 100, and I can support at most, say, 50 members. So now the application at least knows what the level of support is. It supports collectives, and it supports the operation that it needs. At this point, all the peers have to create their address vector sets. So in this case, it creates an AV set. It says, I'm going to start at address 2, end at address 100, stride at 2. So these are just attributes to create the initial set. So he's going to get endpoints 2, 4, 6, 8 up to 100. So it's going to skip every 2. This AV set call, again, that's local. It's going to return an address vector set with these addresses as the starting addresses in it. At this point, this AV set could be modified. You could add in additional addresses one at a time. You could combine it with another address vector set if you had one around. In this case, I'm just starting with one AV set, and now he's ready to join the collective. So when a join operation occurs, it's either on an existing join. So once we do a join, we'll get back a multicast address. And this multicast address can actually be fed into the join call itself. But if I don't have a collective group set up at start, then I actually have to base it off of the universe, in this case, the address vector. So LibFabric has a special address unavailable. This just means that I don't have an existing group. This is the group I'm trying to form, is this AV set, but I don't have an existing group set up as my first join. That's all this syntax is trying to show. So that means that the join operation is actually involving all of the universe. So everybody in the address vector will have to do this join call, and then the AV set will represent the new members. So the output of the join call is, again, a multicast group. This is just a reuse of an existing object in LibFabric. So we get this multicast group coming back. The join call is a network operation. So this doesn't complete immediately, it completes asynchronously. So the second part here is actually the application, in this case, blocking until the join completes. So he's just waiting for an event on the event queue for the join to complete. He checks his event, it says join complete. So now he knows that this join is done. And finally, you can go ahead and provide the collective call. So he just calls the all reduce operation. We have a set of collective calls, all reduce, broadcast, all to all, and just a direct mapping here. So we have an all reduce call. He provides his input data, where he wants the results to go. The multicast, he wants the address of this multicast group that's where the all reduce is going to, and then additional information about the operation, like his data type is float, and then he's wanting to perform a sum operation with the all reduce. So the use of the API isn't too difficult to follow, at least I don't think so. It should map fairly well to applications like MPI, something like Nickel or 1CCL should be able to map to this fairly well. And we do have examples where we have MPI mapping to these type of calls, and then actually using a provider with offloaded collective support. So other thoughts? I have some time. So when we look at these mappings, one of the things that came up in discussions was there may be a limit to how many collective calls can be supported in the network, right? Each in-network call, we're talking about the data types that need to be stored there. We have to distribute the data. We have to collect acknowledgements. And if we're doing this in the network, that means somewhere we're using memory in the network to perform this operation. And we may be limited on how much memory we have or how many active collective calls can be in progress in the network. And how do we manage that? So right now with these APIs, there is no way for the application to know that if I submit 5 all reduce operations, that's fine. If I submit a 6 operation, the 6th one won't be able to run until the first 5 complete. And there's no way for the app to know this until they actually go to submit the 6th operation. And at that point, it may be that the provider just stores it until the network's free and then submits it. It may be that the provider simply says, returns a failure saying E again, I can't start this operation now because the local, the network resources are busy. So one of the proposals I have here is can we create some sort of resource token that's related to collectives? Again, I don't know what this exactly would look like, but before the application submits a collective, can we make it get a token? And then it would know up front whether or not it can actually submit the operation because it has to have a token to do that. And it could be that different operations require different levels of resources. So the network may be able to support like an all reduce or an all to all operation, but maybe only 10 of those at a time. But if we look at something like broadcast, it may be able to support 100 broadcast operations at a time. And the number may vary based on how many peers are using it, right? It may say I can support thousands of all reduce operations at a time if you're only talking to say 4 peers. But if you're talking to 1,000 peers, maybe you can only support 10. Right? So is there a way for resource tokens to try to kind of capture this so that the application can know I have 100 tokens, but if I perform this all reduce operation, that consumes 10 of my tokens. And if I perform a broadcast, that consumes only 2 tokens, right? So I don't have this defined. I think this is just maybe a way to explore as to how can we have these efficient mappings to give the application more control over which collectives it wants to accelerate with offloads versus which collectives does it want to say, I don't want to use my token on this one. I'll just run this collective myself. And that also feeds into like a priority. So certain collectives may need priority over another collective. Like you can start a collective, but then the application finds that, hey, here's another collective I need to run, and I want this one to bump one of my previous collectives. How do we convey this priority? So LibFabric currently only has priority at an endpoint level. It doesn't have priority on a per operation level. Is that something that we would need to add? Is we can say this collective has a higher priority so the provider can do something. And then it's also, what does that mean if you say, I have a lower priority collective running and I have a high priority one that wants to bump it? What does that mean? Does that mean that the low priority is paused and then can resume automatically? Does that mean that the low priority collective is aborted? So I don't know how we can specify priority through the API, but we need to be able to figure out how do we actually convey to the application what the behavior is. If they send a higher priority collective, what are they expecting from the network? Is the network going to just support what they're doing, or is the network going to be able to pause and resume it? And does that work with resource tokens? So if we have resource tokens, are we giving the priority basically to the application to manage, to where if they've used that token, that means it's going to go ahead and complete, versus if they have a higher priority collective, they need to reserve tokens for that. So another thing looking at is whether the results are reproducible. So when especially when we're talking about floating point data, the order that you apply an operation in can change what the output is, so that the results aren't always completely consistent. Typically with collectives, what you want to be able to do is run a collective, get a set of results, run it again, and get the exact same results. But if we're talking about in-network accelerations, it may be that the order that the data shows up at an accelerator, maybe in the switch, the order the data shows up in the switch means that either the switch has to wait until it has all the data from all the peers, and then apply the computation, or it's going to need to, as the data comes in, apply the computation as each peer provides its data. And the advantage of the second case, if you can apply the computation right away, it needs less storage, right? It doesn't need to record all the data and then apply the computation. It can actually do the computation as it's coming in. So is this something that we can expose through the API, is for the application to say, I relax my reproducibility. So right now, LibFabric doesn't define whether it's reproducible or not on the results. That's really going to be up to the provider implementation. But if the application can actually say, I need to be reproducible or relax it, then how do we expose that to the API? Is it something that we can specify when we do like a join? And say this whole collective group doesn't need to be reproducible? Does this need to be on a per collective call? Or is this something that can be fed into like this resource token type of concept? Other things like sparse data. How do we avoid sending and storing a bunch of null data if we're sending a large array? And then this is maybe we just need some sort of compact data aware scatter gather list to say, we did maybe add a stride, for example. So start here, here's my data, but only send every third entry or every fourth entry so that we can compact the data and actually send the nulls across the network. And the last two, almost out of time, so I'm going to just skip these. So these are other areas. Do we need to have network topology? And then how do we deal with programmable? So most of this talk has been about collectives, which have a fairly well-defined set of operations. But if we had other operations we wanted to support, how do we expose that upwards through LibFabric? And I will stop here because I have the other presentation to switch to. Is that their questions?
So we have two questions queued up here. One says, an interesting question would be, what entities resources is the resource and priority token representing? If it's a large disparate network, then a homogeneous evaluation is itself hard, as we've seen with building multicast networks.
Yeah, so I haven't thought through that enough to think about it. What I was thinking with the resource token is, again, it's going to be provider specific as to what it represents. But my thought was the token would be some sort of limiting factor relative to which collectives you could call. So something like a given collective consumes so many tokens, and what that token maps to, the application doesn't care. It just knows that I have 100 tokens, that this collective call would be half of them, or this collective call would be 10 of them. Again, that we would have to have more discussion on what this does and how is it useful to the application, and is it something that can be implemented by the providers?
Okay. And another question, I can see how the various MPIs can use this interface. You mentioned that NCCL and OneCCL maps well to this, but I did not think that upstream NCCL let network providers take on collective group management. Has this changed recently?
So I'm not as familiar with the nickel. I know like with OneCCL, which is kind of somewhat of an equivalent, the OneCCL can actually map and call MPI calls. And then the MPI can use like the offloaded collectives. So I know that there's at least with the one CCL path that actually will take advantage of these APIs to be able to leverage some of the offload collectives, like through like NVIDIA Sharp. I think I can actually map over those sort of offloaded collectives.
And Brian notes that Nickel is still pretty limited to just the simple send and receive interface. Okay. Anything else we would like to talk about on this particular topic? Okay. Thank you.